All right, so this is going to be a review video for both tonicity and water potential. For those of you who were not in class, this is going to help you answer the math portion of your Albert homework. For those of you who were in class today, this is going to be a good review for you. So our bell ringer today was just a really quick review of tonicity. So if a cell is placed in a hypotonic solution, the water will move into the cell. If it is placed in a hypertonic solution, it will move out of the cell. And if it's placed in an isotonic solution, it will move both into and out of the cell. It's important to remember that, number one, cells always will try and reach what is called dynamic equilibrium. Dynamic meaning constantly moving, and equilibrium meaning relatively the same. So dynamic equilibrium is water moving both into and out of the cell, but remaining relatively the same. The second thing that's important to remember is that water will always move from hypotonic to hypertonic. So water potential and tonicity. So tonicity review, hypotonic is lower concentrations of solute, isotonic is equal concentrations of solute, and hypertonic is higher concentrations of solute. I'm going through this quickly because this PowerPoint is on our class notebook. So we can see that in isotonic cells, the cell remains more or less the same size. Remember, water is moving into and out of that cell to maintain that dynamic equilibrium. Hypotonic, water moves into the cell, and hypertonic, water moves out of the cell, from hypotonic to hypertonic. So tonicity and mass changes. So this is going to seem super self-explanatory, but it's not a way that you've really thought of this before. So water has mass to it, it has a weight to it. So when water moves into and out of the cell, the mass of that entire cell is going to change. So if water rushes into a cell, so you place it in a hypotonic solution, remember it's always going to go from hypotonic to hypertonic, the mass of the cell will increase. So water is going in, that mass increases the mass of the whole cell. So if we were to graph the change of that mass over time, the graph would be linearly positive. So as time went on, the mass would continue to increase as long as that cell remains in a hypotonic solution. So for hypertonic solution, you're going to have exactly the opposite effects happen. So if water rushes out of the cell, it is going to decrease in mass. And over time, if you kept that in a continual hypertonic solution, it's going to decrease in mass. So our last one here is isotonic. So isotonic, you can see there in the graph at the bottom, will have no change in mass, so it will remain constant over time. And that's because water is moving both into and out of the cell. The mass of the cell is going to stay relatively the same. You may have at any given second or moment in time a slightly higher or slightly lower mass, but overall the average mass is going to stay the same. So if we take a look at our graph here, what this is the relative change, and instead of mass, or instead of length here, imagine that says mass. Sorry, that's terrible. So that says mass, so the change in mass. So if you have a positive change in mass, so this is a positive change in mass, what that means is that you are gaining mass. So you're gaining mass in here. And if we remember and we think back to our last two graphs, you gain mass when it is in a hypotonic solution. So if our line here is above 0 or has a positive change, then you have a hypotonic solution. For down here, below 0, what that means is that you have a negative change in mass. And if we lose mass or have a negative change in mass, that means that it is in a hypertonic solution. hypertonic solution. So if you have 0 change in mass, so no change in mass right here, that means that you are isotonic. Because remember, isotonic, you have no change in mass at all. So where the graph hits where the line hits the graph is where the isotonic point, otherwise known as the internal concentration of the cell. So when you're going to see this is you're going to see this when we do labs to determine the concentration of a cell. So if we take let's say a carrot, and we put it in various solutions of varying concentrations, so we can put it in pure water, we can put it in a 1 molar solution of sugar. Over here in pure water, our carrot will actually get heavier over time. So if we take an initial mass, it will be lighter than the final mass. If we look over here at 1 molar, it will be lighter because the water will have left the carrot. And we'll have each of these data points for things that we measure. And you'll notice that we never get exactly on this 0 mark. Instead, we use our line of best fit to see where it would cross the x-axis, where it would be 0, so we can figure out what our internal concentration or our isotonic point is that way. So we can do a couple practice problems here. So if I start with pure water here, and it gains 3 grams, then in pure water it will gain 3 grams. So we just go ahead and draw a line down here. So as you increased the salinity here, the change in mass is going to go just like this. So from 0 all the way down here to 0.7, you're going to be gaining mass. So this is all hypotonic. So up here we have hypo. And you are gaining mass here. Down here we have hyper. Somehow every time I do this I get worse. Hypertonic, so it's losing mass. And we can see that for this particular experiment, the internal concentration or the isotonic point is 0.7. So if we do a different example, for this particular line, we still have hypotonic up here, hypertonic down here. But for this one, it's going to be 1 point. Let me just erase that. So it's going to be 1.123. And that's going to be molar. So that is how you use those graphs to determine your isotonic points for this kind of thing. So water potential. So water potential is the amount of potential energy in water, or how badly water wants to move. So if you have a really high water potential, so let's say 0, because pure water has a potential of 0. If you have a really high water potential, it wants to move across that membrane really, really badly. Now, water will always move from an area of high water potential to an area of low water potential. That is why I had you guys really chant in and remember that water moves from high water concentrations to low water concentrations. It was so that this concept made more sense. Now, pure water has a water potential of 0, and we will see why that is when we get to the math section a little bit later on. But pure water has a water potential of 0. That's just a good fact to remember. So the ability of water to do work. If water has anything in it, so ions, water, polar molecules, any sort of solute, then it will form a water shell around those molecules. So here we have all of our partial negatives surrounding this sodium ion. So these water molecules are no longer able to do anything else because their job now is to dissolve that water molecule. So they can do less. So the whole solution has a lower potential because some of it is doing a job, some of it's doing something else. So if you have any solute in your water, then you lose some of the ability of that water to do work. Because of this, water potential is always, always negative. The only time that it is not negative is when you are looking at pure water, and pure water there is going to be 0. So we look at our math and our equations. This font is a little bit weird, so I'm going to attempt, I don't think this is going to be any better, to rewrite some of this. So the solute potential of a solution is how much the solute lowers the ability of that water to do work. So our solute potential is psi, Greek letter psi, sub s, so you'll hear psi s, is equal to negative, and remember that negative is super important because it always lowers the ability of water to do work, I C R T. Now, this looks like a really weird, intimidating equation, but if you break down the pieces of it, it's not too bad. So C, we'll start here. We're going to skip I, as I is the wonky one. So C is just the molar concentration, so you will have that, or you'll be able to figure out that molar concentration pretty easily. R is a pressure constant, always going to be 0.0831. This is on your AP formula sheet. If I give you one of these problems on our unit test, you will see that constant on there. And then you have T, which is temperature in Kelvin, and once again on your unit test, it has the conversion from Celsius to Kelvin. Now let's talk about I. So I is the ionization constant, and that's essentially how many pieces it breaks into when you put it in water. So let's use NaCl as an example. So NaCl is an ionic compound. So when you split it, when you put it in water, it breaks into sodium and chloride. So it breaks into two separate pieces. So its ionization constant, or its I value, would be equal to 2. So something like glucose that does not dissolve in water, that stays in one piece, is going to have an I of 1. And pretty much those are the two that you're going to use. You're either going to use glucose, sucrose, something like that, whose I value is equal to 1, or you will have an I value equal to 2 because you're talking about salts. And again, these I constants for both glucose and for this salt is going to be on your AP formula sheet. So our last formula here is actually for water potential, and it looks super weird and super complicated. You've got psi is equal to psi p, or the pressure potential, plus psi s, and remember psi s will always be negative. Negative. There's an E on that. So it will always be negative. So this whole water potential is going to be negative. And so you'd think, okay, well, we have to have another whole equation for psi p, or pressure potential, but for the most part, it will always be 0. Your pressure potential is going to be 0, with the exception of in plant cells. And we'll do a practice problem that involves calculating our pressure potential for plant cells, but for the most part, it's always going to be 0, unless explicitly stated. So that's kind of a review of your pressure and water potential. I'm going to upload a separate video with some practice problems from your Albert, so I suggest watching those because you'll be getting some answers. Hope you guys have a good fall break, and I will see you when you get back.